Hello, today we're going to talk about the Henderson-Hasselbalch equation. Okay, so when you have a buffer, you're going to have a weak acid and its conjugate base, or you will have a weak base and its conjugate acid. Either way, you need to know which one's the acid and which one's the base. And we need our units to be in either molarity or moles. For both of them, you need to know the amounts present in your buffer solution. The reason I say it can be in molarity or moles is because you're going to find a ratio. Your ratio is going to be the amount of base over the amount of acid. No matter which buffer system you have, it will be the base over the acid. And I use the molarity here, but if you think about, let's say I have a 50 milliliter solution. The buffer system has to be in the same solution, so you'll have the same volume for each. So if you have, whatever moles of base in 50 milliliters, and whatever volume, whatever moles of acid in 50 milliliters, that 50 will cancel. So that's why it doesn't really matter if you're using moles or molarity, as long as you do the same thing for both. So that you'll have a ratio of the base to the acid. We can calculate, using what's called Henderson-Hasselbalch equation, the pH of a buffer solution if we know the pKa of the acid, so whether it's the weak acid or the conjugate acid, but it must be the Ka plus the log of the base over the acid. So the log of this ratio here. So you can solve for that pretty easily. Now, occasionally they'll ask you to find the pKa, or they'll ask you to find the ratio. So you just have to solve for whichever part that you're missing. If they do ask you to find the ratio, so let's say you have a pH is 4, and our pKa is 3, just to make some easy numbers. Well, my pH is more than my pKa, so I know that I'm going to have more base than acid. But to solve for that, you need to subtract the pKa over first. So you'll have 1 equals the log of base over acid. This is always log base 10, just like with our pH calculations. So to rearrange this, it would be 10 to the 1 equals the ratio of base over acid. And so it just happened to work out that, this is just 10. But now you know that the base is 10 times more present than the acid, which makes sense because you have a 1 pH difference. So just be aware that you might have to rearrange the log to solve for that. So that's how you use the Henderson-Hasselbalch equation. Okay, so don't forget that you can convert pretty quickly between Ka and pKa. Let's do it this way, Ka and pKa. pKa is equal to the negative log of the Ka, or 10 to the negative pKa equals the Ka, if you rearrange the log. So you definitely need pKa for Henderson-Hasselbalch equation. Also, another thing that's useful is if you know the pKb of the base, you can find the pKa of the conjugate acid because they add up to 14. pKb plus pKa equals 14. Same thing when you have a conjugate pair, is that Kb times Ka will give you 1 times 10 to the negative 14. So you can solve for that. Just remember that these two must be conjugate pairs. Okay, they must be conjugates. Same thing with pKb, pKa. It only works when they're both conjugates of each other. And you must have pKa for Henderson-Hasselbalch equation. Okay, so let's talk a little bit and relate this to titrations. So let's look at our titration curve really quick. When you have a titration like this, that space between the starting point and the equivalence point is called the buffer region. So that means you can use Henderson-Hasselbalch to calculate the pH during that region. Okay. We already know the pH is equal to the pKa here at half equivalence point. Let's look at that. Here's Henderson-Hasselbalch equation again. pH equals pKa plus the log of the base over the acid. And we know that half equivalence point, these two are equal. So whenever you have equal amounts of the base and the acid, that's a 1, and the log of 1 is 0. So log of 1 is 0, it's just pH equals pKa. So that's why this half equivalence point is so useful. So that's a really common one that they'll give you. Always check to see if it's at half equivalence point first, because that will be so much simpler than trying to calculate for any of the other points. If it isn't any of the other points, then you need to do a BCA chart. So you'll do your weak acid is reacting with a strong base to form your conjugate base and water, and your BCA chart like this. Water doesn't matter. We don't have any of the conjugate base to begin with. Let's say, for example, we have 4 moles of the weak acid and we're adding in 1 mole of the strong base. So I know it's before equivalence point, and I know it's not at half equivalence point. So I'm going to completely use up this added strong base. So at this point in the titration, I will have 1 mole of the conjugate base, none of the hydroxide, and 3 moles of the weak acid. Now that I have the moles for the acid and base, I can use Henderson Hasselbalch. pH equals the pKa plus the log of the base, which is the 1 mole, over the acid, which is the 3 moles. And I'm just making, this is a generic acid, so you'd have to plug in whatever the pKa is for that acid and solve for the pH. And I know because I have more acid, it's going to be somewhere in this range before the half equivalence point. So that's how you would solve during a titration. Let's do a quick weak base example. Half equivalence point, This is still the buffer region here. Pay attention to if it's at half equivalence point, the pH is still equal to the pKa at that point. But remember, the pKa, that's for the conjugate acid of that weak base. So if I have a weak base B reacting with some strong acid, it's going to form Hb+. You could also write this as it's reacting with hydronium to form Hb+ and water. So either way you write that reaction is fine. You need to do a BCA chart. And we don't have any of the conjugate acid to begin with. But let's say I have 4 moles of the weak base and I'm adding in 3 moles of a strong acid. I'm going to completely use up whichever one's smaller, which is the strong acid. And everything is stoichiometrically equivalent. So 3 moles, 0, and 1 mole. From here, you can use Henderson-Hasselbalch equation because I have the base and its conjugate acid present in the solution. pH will be pKa plus the log of the base. Base is this one, over the acid. Don't forget that this is the pKa for Hb+, the conjugate acid. You can't use pKb in this equation. So just be careful of that. And that's how you do buffers with weak bases. Okay, so this one is just a created buffer solution. It's not a titration. We have a buffer solution if the concentration of the acid is 0.137 molar and the concentration of the base is 0.972. And they give you the Ka for the acid is 1.51 times 10 to the negative 5. First thing you need to do is take the negative log of that Ka value, and you'll get the pKa is 4.821. Then we can use Henderson-Hasselbalch equation. pH equals that pKa plus the log of the base, which is 0.972, over the acid, which is 0.137. Notice that the base is a lot higher than the acid, so I know that the pH will be greater than 4.821. So, and when you actually solve, take the log of this ratio I divide first, then I take the log, then I add in the pKa, and you'll get that the pH is 5.672, which is larger than the pKa, so you know you did something right. Okay, this one wants us to calculate the Ka based on the following information, and I give you the pH of the system is 4.219, and the buffer has 2.43 moles of acid, 1.75 moles of this stuff, which dissociates and becomes your conjugate base. And it's dissolved in 1.92 liters of solution. Remember that the volume doesn't really matter because it's the same volume for both of them. So we can use Henderson-Hasselbalch. The pH we know, 4.219, but we don't know the pKa. And we're going to do the log of the base over the acid, 1.75 for the base and 2.43 for the acid. So I'm going to take I would divide first and take the log, then subtract it from the pH, and I will get the pKa. And I would get 4.362. Just to remind you, because this is a fraction that is less than 1, when you take the log of that fraction, you'll get a negative number. So when you subtract a negative, this number actually increases. And that makes sense because I have more of the acid in the solution, that the pKa will be larger than the pH. And then from here, all you need to do is to do 10 to the negative pKa, or 10 to the negative 4.362, and that will give you your Ka value, which is 4.35 times 10 to the negative 5.